Unit 10, Worksheet 3, Coulomb's Law. Problem 3. The most common isotope of hydrogen contains a proton and an electron, separated by about 5.0 times 10 to the negative 11th power meters. The mass of a proton is approximately 1.7 times 10 to the negative 27th power kilograms. The mass of an electron is approximately 9.0 times 10 to the negative 31st power kilograms. There are 3 parts to this problem. The first part, we're going to determine the force of gravity between the proton and the electron inside of the hydrogen atom. Then, after that, we're going to use our 1.6 times 10 to the negative 19th power coulombs as our charge for the proton and our charge for the electron to determine the force of attraction or the electrostatic force between those two particles. Before finally, we're going to be comparing those two values by determining how many orders of magnitude there is between those two forces to determine which one has a greater effect on keeping that atom together. So to start off with, we're going to make a list of our variables. So in an atom, we have our proton. Protons are positively charged. Those are at the center of our atom in the nucleus. Surrounding that is going to be our electron that exists in the cloud that orbits or surrounds the nucleus. For this problem, we are told a mass of our proton, which is 1.7 times 10 to the negative 27th power kilograms. We're also told our charge of our proton, or any of these elementary units of charge, is going to be 1.6 times 10 to the negative 19th power coulombs. And then because it's a proton, it is positive. For our electron, it is significantly lighter. The mass is 9.0 times 10 to the negative 31st power kilograms for the mass. And for the charge, it is negative 1.6 times 10 to the negative 19th power of coulombs. We're also told that we have this as our radius separating the two values. So for the first part, we're going to use the law of gravity. So our force of gravity is equal to mass 1 times mass 2 times a gravitational constant divided by the radius between them squared. For this one, the mass of our proton is 1.7 times 10 to the negative 27th power kilograms. The mass of our electron is 9.0 times 10 to the negative 31st power kilograms, and that capital G is our gravitational constant of 6.67 times 10 to the negative 11th power newtons meters squared over kilograms squared. And then all of that is going to be over the distance between these two, which is going to be, in this problem, 5.0 times 10 to the negative 11th power meters, and make sure we remember to square that. When we plug this into our calculator, we can determine that the force of gravity that is acting between the proton and the electron for this problem is 4.08 times 10 to the negative 47th power newtons. So it's a very, very, very small force of gravity. Now for part B. Just going to give myself some space to organize there. We're going to be using Coulomb's law as our force of attraction to determine how strong that force is going to be. Fe for electric force, charge 1 times charge 2 times Coulomb's constant, all of that divided by the distance between them squared. So our charge of our proton is positive, 1.6 times 10 to the negative 19th power coulombs. Charge of the electron is negative, 1.6 times 10 to the negative 19th coulombs. And Coulomb's constant is 9.0 times 10 to the positive 9th power newtons meters squared over coulomb squared. And then they're still separated by the same distance of 5.0 times 10 to the negative 11th power meters, and once again, square it. When we plug this into a calculator, the value that we get is 9.22 times 10 to the negative eighth power. So these two things are very, very different. That negative eighth power means that we would shift that decimal to the left 8 times for our force electric, whereas in our force of gravity, we would shift it to the left 47 times. So it looks like our force electric, while small, is still significantly larger than our force of gravity. Part C, we're actually trying to determine how many orders of magnitude greater is our electric force than our force of gravity. And the reason why we're doing that is to determine how important our gravitational force affects in this case. So for part C, our electric force divided by our gravitational force, or the 9.22 times 10 to the negative 8th power newtons over 4.08 times 10 to the negative 47th newtons. Newtons cancel out, and then the value we would be left with is going to be 2.26 times 10 to the positive 39th power. Now for this problem, that exponent right there is going to be how many orders of magnitude we have. So Fe is 39 orders of magnitude greater than our force of gravity. Now, if it's 1 order of magnitude greater, that means that one force is 10 times larger than another force. If it's 2 orders of magnitude greater, that'd be 100 times greater. 3 orders of magnitude, 1,000 times greater. This right here, our electrostatic force is 39 orders of magnitude greater than our force of gravity. What that means is our gravitational force is kind of insignificant in holding our proton and electron together in the most common isotope of hydrogen.